Hello and welcome to our sensor simulation models booth. Within the next minutes we will present the models of perception sensors that were developed within the level project. We covered all the major technologies from camera, radar and LiDAR sensors and have different modeling approaches that will be presented here. All the models are connected via the OSI interface and are packaged as an FMU, so they can be modularly applied with different simulation tools and different use cases. We will start with an object-based model. This model is for both LiDAR and radar sensors. It has an object input and an object output, so it's solely relying on the objects. And here we get the ground truth as an input via the OSI. And then we have a unified modeling framework. This image you will see also on the next slides and the next models, because the interface going in and going out is always the same. And here in this particular model, we simulate the front end, covering effects like occlusion, for example, if one object is behind another one and occluded or partly occluded. And we also have an approach for kind of refined bounding boxes, so we don't have only the rectangular ones, but a little bit more refined to the actual shape of the vehicles. And then from that we extract the detected bounding boxes. This is shown here, so we have the blue ones, those are the detected and tracked by the model, and the gray ones are basically the model input, the ground truth coming from the environment simulation here. The next model is not object-based but reflection-based. It's a reflection-based LiDAR model. This means that from the environment simulation we get individual reflections coming from a ray tracing algorithm, and we take these reflections as a super sampling, and from there we calculate detections. This is visualized here, again the same framework, but now next to the objects we also have reflections, or it's called in the enhanced OSI we developed in set level, the rendering results. So this comes from the rendering, and we use it to do our detection sensing. So we do thresholding, we're capable of calculating multiple echoes per beam. We can calculate intensities, echo pulse width, all depending on the sensor that's simulated. We transform it to object coordinates, so to ego vehicle coordinates. And then we also have a tracking simulation. I would refer you to the booth B2-3, where this is explained in a little more detail. And at the end, we output detections, so the classical point cloud that's seen here in the colored points. This is the point cloud output. And because of the object tracking we also have tracked objects here, which are the blue boxes, same as you've seen before, but here based on the simulated LiDAR point cloud. The next model is also reflection-based, but it's a radar model, not a LiDAR model. And here again the same framework, same overall concept. The difference is that we have a radar rendering, radar ray tracing beforehand as an input, and we do radar typical effects like windowing, interference, we do our peak detection, bin interpolation to come to the detections. Also here visualized as the colored points. And then same as the LiDAR, we also have a tracking simulation visualized as the blue boxes in this visualization here. This concludes the radar and LiDAR part, and now I would like to hand over to my colleague for the camera simulation.
Thank you. Yes, let me introduce to you the concept of image-based camera model implementation. We are obtaining from our environment simulator our ground truth information using the interface sensor view. We obtain the ground truth information for the image pixels, the depth, the object list, and the optical flow. And the input is via OSI to our SMI1, which is our camera sensor model, with our specific camera effects like maybe blur, distortion, imager noise, for example, which is implemented. Afterwards, we have our FMI2 camera sensor model for our image processing, for our depth detection, for object detection and optical flow, where you can see here the videos. Afterwards, you can apply different metric KPIs here using MATLAB or Python scripts to evaluate your quality of your sensor model implementation. And the other approach is to implement an object-based camera model where your input is really an object list using the interface OSI3 sensor view with a list for moving objects, stationary objects, traffic lights and traffic signs, and also more objects. Coming from IPG CarMaker or DSpace ASM, using also the interface OSI3 sensor view. Within the object-based camera object model, you first have a coordinate transformation where you transform your objects into a specific camera coordinate system, then apply different camera effects, which we implemented here phenomenologically. So we implemented different uncertainties. For example, the existence uncertainty, which is an uncertainty where an object captured by a sensor really exists, caused by detection uncertainties due to a limited field of view, limited range, or limited occlusion or occlusion. Furthermore, we implemented state uncertainty for state variables such as object position, object velocity, caused by stochastic measuring error of the sensor technology, and also state and existence uncertainties for tracking and class uncertainties. So uncertainties if a truck is a truck or a passenger car or a bus. Here below you can see some videos where a car is approaching a crossing and detecting different objects like moving objects, traffic lights and traffic signs. And here in the video you see a pedestrian which is detected in the case when it's in the field of view of the camera. When the car is moving on, the pedestrian leaves this field of view and is not detected anymore, so the bounding box is not visible anymore after he leaves this field of view. So that's everything from my side, and I will hand over now to my next colleague.
I can present you the last sensor model. It's a triangle-based radar reflection model, and compared to the previous model that output an object list, here reflections are output, and each reflection consists of an azimuth, elevation, time of flight, but also about an electric field strength, and that one is then radar specific. The input for the model is a ground truth map, so a list of objects, and each object is associated with a 3D model, something similar you see here. And then the triangular-based radar reflection model is emitting rays, hitting the object, and also follows indirections throughout the models. But for the backscatter, it uses a physical optics calculation that really emulates the wave characteristic of a radar sensor. You see it here, for example, each triangle hit, these are the violet ones, are contributing to the backscatter. And that allows us to calculate an electric field strength based on the hit triangles. The model takes, for example, into account the surface normal, so if a triangle is looking away from the sensor, it's not contributing to the backscatter, for example, here these green ones. And that concludes the overview about the sensor models in this booth. Thanks.